let's continue. This is part 6, differential geometry. Attention now, extrinsic geometry, 3D. Okay. Now this lecture 4, I will show the covariant derivative, definition and notation. Now we will define the Christoffel symbol of second kind. Now consider vector V, okay? Vj are the contravariant component of this vector V, and A sub j is the basis vector of the covariant basis vector of the same space vector here. You see, this is Aj, Vj, and Xi. Xi are the contravariant coordinates. All of these belong to the space vector V, not the dual, okay? That's a space vector V. Now, the covariant derivative of the vector V, attention now, V is a first order tensor, okay? Remember the scalar is zeroth order tensor, and there is a tensor of second order, third order, and so on. So V is first order tensor with respect to Xi, the upper indices. This by definition, okay? There is no question about this. By definition, you see? This is by definition. You see, this is several notations represent the same idea. This is partial derivative with respect to Xi, okay? This, in general, in the literature, you find this is nabla here, nabla V. This is covariant derivative. That also, this is represented by capital D, dV of the Xi. You see? Now I substitute V here by the contravariant component and the basis, covariant basis vector. Okay? Now attention now, that's a very important consideration, because you see, when you have a curve, you look at here, you see, for instance, this is C1 and C2. This is A1 and A2, the basis vector. Now if you change to another point, you see, if you change to another point, there will be others. The basis vector, this point Q, this basis vector change. You see, this is C1, see this C2, okay? I'll put over here. This is another, this is C2. You see, the basis vector here changes, okay, when we move from one point to another in a curved space, okay? That's why this I have the product, okay, the product rule, okay? Derivative of the first one with respect to Ci, Aj, plus Vj, partial derivative of Aj with respect to Xi. I call this expression 1, okay? You'll say this is notation, okay? The literature you find many different notation about the same quantity. Now, consider the term related to the curvature surface. Attention now. This term of here, okay, is related to the curvature. If there is no curvature, like for instance when you treat in Cartesian coordinates, okay? So in Cartesian coordinates, the basis vector, okay, doesn't matter, it's a covariant or contravariant, okay? They coincide. But the base vector doesn't change when you move from one point to another. Okay? So when you have in the Cartesian coordinates, this term here will be 0. Okay? That's important because this will be constant. Now, then consider only this term over here. We're just going to work on this term over here, which is responsible for the curvature. Okay? And the basis change when you move, when you change points, the basis vector change also. So that's why I have this term over here. It's a very, very, very important. Now, you see, suppose I have C1, C2. You see this vector, a base vector A1, a base vector A2. Okay? This is tangent to this curve. A2 is tangent to this coordinate line. Now, this is a linear combination, okay, of A1 and A2. So this will be alpha A1 plus beta A2. See, I can represent this vector over here, okay, as a linear combination of the basis, the covariant basis vector here. So I will define, by definition, okay, alpha, this constant alpha here is capital gamma 1 ij A1, and beta is capital gamma 2 aj A2. Now, attention now, see 1 here is the upper indices. A1 here is lower indices. Likewise, 2 here and 2 over there. See? So I substitute just alpha and beta over here. Then I can combine this term as this one. You see? You see, this is a sum. Attention now, M here is dummy because I will have gamma ij1 A1 plus gamma ij2 A2. It's just like this. Okay? That's the sum over there. So this is a Christoffel symbol of second kind. Okay? So then I can write, okay, this is the second term, this is the second term over here, the second term, and this I can write the second term like this. You see, Vj, A sub j, Ci is Vj, Christoffel symbol Am. Okay, I just substitute here on this definition over here. You see, I substitute this over here. I maintain this the same. So I just wrote here. Now, remember, recall an important property. Partial AI Cj is identical. I already showed this in previous video. That's a partial Aj respect to Cj. See? Let me put it here. Pardon, Cj, Ci. Okay, I just swap. Okay? So, gamma ij is identical to gamma ji. You see, this is symmetric with respect to j and I only. No. Thus, I can, since j and m are dummy, you see, I can play a little bit here. You see, Vj gamma ij m. You see, I can, look, this is j, the blue one. Okay? I can substitute Vj by Vm in m over here. Okay? Now, I can substitute m as j. It's quite easy because m and j, they are dummy. Okay? Let's put here in the plural. Okay? Are dummies. See? Now, you see, just easy, okay? then I can write, you see, this whole term, attention now. You see, AJ over here is not confused because I just changed the indices, the undummy indices, just to appear AJ over here on the second term, because there is AJ here on the first term. So I can factor, you see, this parenthesis AJ, okay? You just look here, substitute here, will be appear here AJ, you see? So AJ that multiplies this and this is the covariant derivative. Now, you see the component is the covariant derivative represented by its components, okay? Nabla sub I Vj. See, this is a covariant derivative expressed in terms of components. And don't forget, this is the same as this, partial Ci Vj. You see this notation over here is the same notation over here, okay? So here is the components, okay? The components of the covariant derivative, okay, we can represent as two different terms, okay? This is a partial derivative and this is a contribution, attention now, for the curvature. If there is no curvature, okay, this will be 0, so, and then I have only this partial derivative over here. Okay, this is a covariant derivative, attention now, of a vector, a first order tensor, okay? There are covariant derivative of second order tensor, third order tensor, and so on. You see, I think this that's clear. Okay.